Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to show a theorem that has to do with the distribution of a function of random variables that are normally distributed. But before we provide a mathematical proof of that result, why do we care about such results? Well, in statistical applications, it is often assumed that the population from which a sample is taken is normally distributed with parameters mu and sigma squared. So there is then an interest in estimating these parameters mu and sigma square, or we are interested in testing some conjecture about these parameters. The usual statistics that are used in these activities, right, if we want to say something about mu or sigma squared, right, the statistics that are used are the sample mean x bar and the sample variance s squared. So we need to know something about the distribution of these statistics or functions of these statistics. Make sense? Okay, so the result, the theorem that we're going to be showing, is a step in that direction. So this is a theorem from our textbook, right? So we have a random sample of size n, okay? So y1, y2, and yn are identically distributed. They have the same distribution. They come from a normal with mean mu and variance sigma squared, and they are independent, okay? That's what we mean by a random sample, okay? So now we use them to form a transformation, right? To form this quantity, the sample mean, y bar. And it's just the sum of the yi's divided by n. So what we claim is that the distribution of y bar is normal, again, that is preserved, and the mean for this transformation for y bar is mu, and the variance of this transformation, y bar, the sample mean, is going to be sigma square divided by n. Okay? Well, let's show that result. Proof. So, do you remember in sta258 we talked about MGFs, and we said that MGFs, moment generating functions, were going to be very important to show some theoretical results in statistics. So this is an example of such a result. We're going to employ the an MGF, and we're going to be using the uniqueness of MGFs to show this result. Okay, so by definition, let me remind you what would be the definition of the MGF. Remember that it's the expected value of a very particular transformation. So we use the capital letter M to refer to the MGF, the moment generating function. Let me be very specific about this with my notation. We are going to be finding the MGF of y bar. It's the MGF is a function of t, right? And the definition is that it's the expected value of e to the power t, in this case times y bar. Okay. Not what I want there. Let me type it there. Looks better that way. Okay. So now let's use just, you know, the way that y bar is defined. So it would be e to the power t times, let me do it like this, let me use the following notation: exp as in e to the power t times, and I'm going to be using the definition of y bar, right? One way of thinking about y bar is the sum of the yi's divided by n, right? Which would be the same as y1 divided by n plus y2 divided by n, and so on. yn divided by n. Make sense? Just using the definition of y bar here. Okay. Let me make it look nicer. Okay. Then here maybe curly brackets there. Okay. So just expected value of e times y bar is the same as expected value of e to the power t times, and then we have the definition of y bar. Okay. Now just doing a little bit of algebra, what we're going to have here is this, right? This is the same as that t multiplying each of those guys, right? T, 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 right? Make sense? Now, this would be the same as the expected value of, let me copy paste this. We could re-express this, e to the power t times y1 divided by n plus t times y2 divided by n dot 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 t yn divided by n as a product of exponentials, right? So this would be the same as, let me copy this guy, this exponential here, just the exponential, that's the only part that I need. Yeah. And maybe one more. Okay. Now, that's what I meant. We could re-express that e to the power t times y bar as this, and then this, the this e to this exponent is the same as the product of these exponentials. Make sense? Okay. So now what I want you to see here is that by independence, what we have is that the expected value of a product is the same as the product of expected values. So what we have now here is this. Let me use here. Let me copy paste this again. Let me get rid of this guy. Okay. Right? So again, we're using the independence between y1, y2 up to yn, and then the expected value of the product is the same as the product of expected values, right? And again, remember that I was just using this exp notation for this. E to the power e, well, the expected value of e to the power, in this case it's just ty 1 divided by n, right? It's the same, right? And then I have the other one. Now I have y2 dot 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 and then yn. Okay? Now note that the expected value of e to the power t times y1 divided by n, that is by definition, right, the MGF of the random variable y1, but instead of the MGF being evaluated at t, is being evaluated at t divided by n, right? Same goes for this one. This would be the MGF of y2, not evaluated at t, but evaluated at t divided by n. So let me copy paste that. Right? Now, let me remind you that I think it's page 837 or 838 of our textbook, where we have a table with the most popular distributions, probability distributions. So the one that we want is page 838, because there we will find the continuous distributions, and that table contains the PDF, mean, variance, and the moment generating function. So that moment generating function is the moment generating function for a normal with mean mu and variance sigma square, but this guy is evaluated at t, and we want to evaluate ours at t divided by n. So we just change accordingly, right? And remember that this is just notation, exp for e to the power mu times t plus t squared times sigma square divided by 2. So let's just make the appropriate change, the one that we want, would be e to the power mu times t divided by n plus t divided by n squared times sigma squared divided by 2. Make sense? So let's write that down here. So it would be e to the power mu times t divided by n plus, right, what we're going to have here is 1/2 of sigma squared times t divided by n squared. Make sense? So that's the MGF for our first guy, right? And we have that n times, right? Because they have the same distribution. So we have this once, twice, n times. Okay? So now let's do the algebra. So we just have to do e to the sum of these exponents, right? So let's deal with the first one. Mu times t divided by n. We're going to have n times that guy, which means that in the end what we will have is e to the power n times mu times t divided by n. So those n's will cancel out. So we will have just e to the power mu, okay, when we add all these up, right? Okay. So in the end we will have that. Okay, now let's deal with these guys, the sum of these guys. So note that what we're going to have here is t squared divided by n squared, right? And we are going to have n of these terms, right? So what's going to happen is that we're going to have n times this. So we're going to have n divided by n squared. So 1n is going to cancel out, but this guy will be t squared. Make sense? Right? Can you see it? Okay. Now, if we compare that with the expression that we have for a moment generating function for a normal with mean mu and variance sigma squared, what we can easily see is that, oh, that MGF we just found is the MGF of a normal with mean mu and variance. Instead of the variance being sigma squared, we could rewrite this as follows, right? This is the same as sigma squared divided by n and then we just get rid of this here, right? Make sense? So that n that divides t squared, now we place it here, so it divides sigma squared, and then we can easily see that what we have here is the MGF of a random variable with mean mu and variance sigma squared divided by n that has a normal distribution. Okay, that would be the MGF of y bar. So by the uniqueness property of MGFs, y bar has a normal distribution with mean mu and variance sigma squared divided by n. And that is exactly what we wanted to show. Make sense? Okay, so just to summarize, what we have realized now is that if we have a sample, random sample of normal random variables, right, and we compute the sample mean, right, so the distribution of the sample mean is going to be normal again, and now the parameters are going to be mu. The mean remains the same, but the variance is going to be affected by the sample size. The new variance, the variance of y bar, the sample mean, will be sigma squared divided by n. Okay? Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.